So aims for today then, using engineering notation, 5 minutes or so on that, just going through a couple of examples. We've already looked at it briefly. Comparing that with standard notation, standard form notation. We need to know what that is, but we tend to stick to engineering notation within the engineering course. I've talked very quickly about where you're going to find video clips on histograms and cumulative frequency curves. So I'm going to leave that there, but that's an aim for today, so that's for you to look at when you get a chance. It's not on there yet, but I aim to get it on there sometime this week, so hopefully by the weekend you'll have it there. What I want to spend the focus of today is on this idea of rearranging formulae. Not something that's going to particularly come in to the assignments actually for Unit 4. So you're not going to be asked to rearrange loads of formulae for this unit. However, I think it's an important skill because engineers use formulae all the time, and it might well be that the formula is not in the right form, so you need to be able to rearrange it. So it's a skill that I wanted to have, okay? A good general skill. So we're going to look at that, and that will also introduce us to the idea of manipulating algebraically. So that's the aim for today. That exercise, as I say, is the one that's going to sort of form the basis for those video clips that I'm going to do on cumulative frequency curve and histograms. So rearranging formulae and engineering notation. Well, let's look at this idea of engineering notation first. Just expand on that. So, a quick note. Engineering notation and standard form. As we've said, take a number like 36 with a few zeros after it, a large number. Can be thought of as 36 times 10 a number of times. If I were to move the decimal point, here it is at the moment, and I were to move it to there, I'd have to times it by 10, 1, 2, 3 times, 6 times, 9 times, 12 times to get it back to where the decimal point should be. So I could write it as 36 times 1,000 or 1,000,000,000 or a billion, the old billion. Or I can write it as 36 times 10 to the 12. 10 to the 12 means 10 times 10 times 10 times 10, 12 times. So that's literally writing this number in shorthand. Or 3.6 times 10 to the, if I move it back one more place, now how many times have I got to move it to get it back to where it should be? 13. So that is standard form. And we always put the decimal point after the first significant figure. So that's standard form. However, in engineering, we tend to stick to engineering notation. So this is engineering notation, where the power is a multiple of 3. So that's the only difference between the two, really. Right. It's a multiple of 3, shorthand MLT, multiple. That's a common abbreviation for multiple. Multiply, multiple. Right, there's a number. Express that in engineering notation. Answer? 18 times 10 to the 6. Okay. Any other possibilities? What's the missing number there? No. No, I can see where you're going, but I've moved it. I've got to move it 6 places from 18 to get back to there. Now I've moved it 3 more places, so 9. You see that? I've moved the decimal point to here, 0.018. Oh, 0.018 doesn't like zeros, so I've got to go back now 9 times to get it back to where it should be. Okay? Or right. Which one's correct? All of them are correct. Yes, all of them are correct. It depends on what you want. This lends itself perfectly to prefixes, which is why we use engineering notation. 10 to the 6 is mega. Whatever units we're talking about. A million. 10 to the 9? Giga. So if I was talking computers, I might well want to know this is 0.018 gigabytes, a common unit within computing. 10 to the 3? Kilo. So I might be talking about units of electricity in kilowatts, so I need to know that's 18,000 kilowatts. Or I might be quite happy for it to be expressed as 18 megawatts. It all depends on what prefix or what units you tend to be using. So they're all correct, and I think that demonstrates why it is that we use engineering notation, because it lends itself to these prefixes. So if you get you're doing a calculation and you get this answer in joules, then you might say, well, actually, that's 18 times 10 to the 6 joules. Or you might say, that's 18 megajoules. All 3 answers would be the same, would be correct. What about this? I think I've done that right. That's actually the charge on 1 electron, roughly. A very, very small number measured in coulombs. Have I done it right? Well, I think so. I was counting as I went along, okay? You wouldn't want to write the charge of 1 electron as that, okay? So you use this idea of engineering notation or standard form. If I want to express this in standard form, I must move the decimal point to there, after the first significant figure. If I want to express it in engineering notation, I can move it anywhere I like, so long as the power is in a multiple of 3. So let's say I'm going to move it from where it is now to there, and let's put this thing in standard form. This time, if I move it to 1.9, to get it back, I'm not multiplying by 10, I'm dividing by 10. And dividing by 10 is, divide by 10 is the inverse of multiplied by 10. So we use this -1 idea as the inverse. -2 means minus or divide by 10 twice. -3 means divide by 10 3 times, and so on. So, as far as you're concerned, we do exactly the same thing. We just count the number of places we move the decimal point, but because we're going backwards, it's minus. So it's 10 to the minus, and this is where I find out whether I've done it right. 19, is it? Which is correct. So the charge on 1 electron is 1.9 times 10 to the minus 19 coulombs. If I wanted it in engineering notation, what would I do? Okay, 0.19 times 10 to the minus 18. Good. Because now the decimal point, and this is something that confuses some people, you know, which way, what do we do? If you think about it, that's where the decimal point is now, and I'm now moving it to here, so one less than I did before, so I'm only going to go back 18 places. Now it's in engineering notation, and to put a prefix on it, I'd need to know what the prefix was that meant minus 18. Not a common prefix. I'm trying to remember what it is. I know femto is minus 15, so it's the one below that, which I can't remember. Okay. The more common ones, though, are minus 3, minus 6, and minus 9, and minus 12. You will use those. So, this is in standard form. This is in engineering notation. And the common prefixes associated with it are 10 to the minus 3 stands for milli. Don't let, and oh, I forgot again. Alan, that's right, don't let Alan sell all of me. 10 to the minus 6, someone else is micro, good. The symbol for milli is little m. The symbol for micro is this mu symbol. If you've not seen that before, or you don't know what it's called, mu, M-H-U. Below that, 10 to the minus 9. Nano. Little n. Back row, 10 to the minus 12. Might have come across it in capacitors. We talk about farads. Anybody? Pico. And we go below 10 to the minus 15 is femto, but we won't be using those. Okay, it's very unlikely. These are the more common ones. We more often want to express very small numbers and very big numbers, so we go down further. However, in the computing world, we're now actually talking about the one above giga, which is tera. Yes, so we talk about terabytes, which is 1,000 gigabytes. So the only other thing now is putting these things into the calculator. So if I want to do a calculation on the calculator using this standard form or engineering notation, what do I do? So let's just do one calculation, similar to the one we did last time in the drill. I think I might have made a mistake actually in my, now I write it down, I'm so used to writing this charge of one electron, actually I think it's 1.6 times 10 to the minus 19, but I was only points, you know, tiny amount out, roughly that. That's the charge on one electron. If I write this number down, I will put a bracket around it. You don't need to put the bracket around it when you put it into the calculator, but if you're writing the number down, just to keep it as a number, use a bracket. And I'm going to multiply that by which is a massive number, 6.23 times 10 to the 23, and that's Avogadro's number, which if you've done any science you might know is the number of atoms in 1 mole of a material. So what we're finding is the number of the charge on 1 mole of electrons. 1 mole, yeah, which is a chemical term. So I want to multiply them together to get a number, which is the charge in 1 mole. And it's called the Faraday number actually, so you could look it up and check you've done it correct. So to enter those onto the calculator, we key in 1.6 and then we hit the times 10 to the x button. So that gives us our times 10 to the. And then we hit a minus button to get, not the minus button that you'd normally press, but there's a key with a minus sign in the bracket, or some of them have a plus minus sign by them. So you hit that to change it to a negative, and then you key in 19. So let me change the color. So 1.6 times 10 to the minus 19 multiplied by 6.23, and again times 10 to the 23. Equals. You don't need to put the brackets in on the calculator. No, that I always put them in on paper so you can separate the two numbers, but actually on the calculator you don't need the brackets. Do you? Okay. Well, yeah, I recommend you get a different calculator. Didn't they? Okay. Anyway, answer somebody?
99.68 times 25.
Okay. 99.68 times 10 to the 3. It's in coulombs if we're thinking about this actual number because it's a charge. So it's 99,680 coulombs. If you want it as a number, because times 10 to the 3 means you just move it 3 places. So for small values like that, you wouldn't necessarily write it in engineering notation. Not necessarily, no, there's no need to. Because, in fact, that's longer than that. So the whole idea is shorthand. So, yeah. Okay. One last thing on this that I want us to look at. So have you all managed to get that answer? Let's just look at it then. Okay. One of the problems with engineering notation and standard form is these are massive or really small numbers. So it's very difficult to get an idea in your mind as to what you expect the answer to be. Whenever I key an answer, something into a calculator, especially if it's a long calculation and you get this number at the end, how do you know whether or not you've made a mistake or not? Unless you do it again, in which case you might make the same mistake again. And so we talked last week about this idea of estimation and how you might come up with a rough idea what you expect the calculator to give you. Well, we can do that with these. What we do is we estimate this. So we can actually estimate this. Let's look at it. And I'd like you to try and do this. Get used to doing this, whether you will or not, that's up to you, but useful thing to do. Round the number to one significant figure. So 1.6 is 2 to one significant figure. 6.23 is 6 to one significant figure. 2 times 6 is 12. So I'm going to expect 12-ish. And then what do I do about the powers? When you multiply numbers together, you add the powers. Minus 19 plus 23. 23 minus 19 is 4. So I'm going to expect roughly 12 times 10 to the 4. 120,000 maybe. I've rounded that up and that down, so 120,000. And I actually get 99,680. So reasonable. Okay, it's in the right ballpark, as they would say in America. So I'm going to expect a quick calculation like that will help me to check whether or not my calculator is giving a sensible answer. When you multiply, you add the powers. So minus 19 plus 23 is 4. Okay? Right. One to have a go at. Pardon? Yeah, that's the Faraday number, yeah. So, okay. Calculation on your calculator. And to do that in one hit on the calculator, use the fraction button, if you've got one, and use the squared button to come up with that in one hit. You might want to put the whole thing in brackets to make sure you're squaring the whole thing. So you're going to be using the bracket buttons. .67 2684. Okay. Appropriate accuracy. What accuracy are you going to give me? Yeah, 3. So give me that to 3 significant figures. Yeah. 5.67 times 10 to the 11. So 3 significant figures. Agreement? So to estimate this answer, round to one significant figure, 2 divided by 3, so round about 0.67, 2/3. Now this is the key bit. When you divide, as we'll see when we look at the laws of indices, you subtract the powers. 18 minus 12 is 6, but then I'm squaring. So 6 raised to another power of 2, again from the laws of indices, means you actually multiply. 6 times 2 is 12. So I'd expect around about 0.67 times 10 to the 12, which is the same as 6.7 times 10 to the 11. So quick calculation in my head, that's what I was expecting to get, roughly 10 to the 11 on the calculator. You don't even need to worry about this bit, the 2/3 bit, just the powers. 18 take away 12 is 6, 2 6 to the 12. I was expecting roughly 10 to the 12. Well, I've got 10 to the 11, but that's acceptable. I've probably not made a mistake on the calculator. Okay? Okay.